In this video, I'd like to discuss probability density functions, the probability and how you would calculate that, as well as the expected value. So with probability for probability density functions, it's a continuous random variable, so you can't pick out a probability for a certain outcome. You have to pick over a range. So here we're asking, what's the probability that x, a random variable, is less than or equal to 3? So to solve that, since we have our PDF defined as an exponential random variable, it's only valid from 0 and beyond. We go down from 0, and then we go up to 3, and then we simply integrate the probability density function. And this would get the probability of, let's say, a light bulb lasting at most 3 years, something like that. So the next thing we could talk about is the expected value of this probability density function. And we solved this as a weighted mean, very similar to how we did with the discrete case. Instead, this time, since it's continuous, we'll use an integral. So we're going to do an integral over all x values. So for us, that's going to be 0 and beyond. You just do that straight away. So 0 up to infinity of x times fx of x dx. And when we go ahead and solve this out, the proper thing to do in math, you do limit as a approaches infinity of the integral 0 to a, and then x times lambda e to the negative lambda x dx. And if you want to watch how to solve the integral like this, I have videos about tabular integration, but I'm going to go ahead and set that up now. I'm taking integrals on this column and derivatives on this column. So taking the integral, I'm dividing by negative lambda, and I have negative e to the negative lambda x. Then taking the integral here, we get 1 over lambda e to the negative lambda x. So then we can write this as the limit as a approaches infinity of negative x e to the negative lambda x minus 1 over lambda e to the negative lambda x, evaluated from 0 to a. So plugging this in, we get negative a, and then e to the negative lambda a minus 1 over lambda e to the negative lambda a, and then minus the quantity 0, since if we plug in 0 for x, it goes to 0 there. And then minus 1 over lambda e to the 0 is 1, so minus 1 over e to the lambda. And still, again, we're taking the limit as a goes to infinity, right? So here we have an indeterminate form, negative infinity over e to the negative. So this is actually e, since I'm bringing it down to the denominator, it's e to the infinity minus 1 over lambda times 1 over e to the infinity. So this term we know can go to 0, but this term is like infinity over infinity, which is a indeterminate form, so we need to take the derivative from top and bottom. So it's negative a over e to the negative lambda a. We need to take the derivative on top and bottom, so we get negative 1 over the derivative here. It's negative lambda e to the negative lambda a. And this term, since a goes to infinity, is going to 0. So we have 0 minus 0 minus 0 minus 1 over lambda. And this whole thing evaluates to 1 over lambda. And I'll show you a graph of the expected value and the probability density function for different lambdas right now. So here I've gone ahead and graphed out this exponentially distributed random variable. L here is going to be lambda, right? And it's only valid for x greater than 0. And we can kind of see L acts as a, let's call it like a rate variable. Because if we increase L, we notice that the rate of the decay happens faster. A lot of times we'll use exponential variables to model things like how long something will last. So that could be something like a light bulb is modeled as a random variable, like its lifespan. So let's say this was years. The light bulb has pretty high probability of lasting a year because it's like the area under the curve represents the probability since it's a density function. And then I've gone ahead and also plotted the expected value. So the expected lifespan, this is also like I talked about in the video about discrete random variables where we found the expected value there. This is the same thing. It's like where do you put your finger that balances? So if I change the rate around, we see that the expected value gets lower. So obviously if the rate of decay is super high, you can expect that the light bulb is not going to last as long. So this is cool stuff. Sweet.